All right, let's try an example of finding the limit of the symmetric difference quotient given the function 2x squared minus 3. So when we're doing this, first things first, I need to have all of my functions to plug in. So we got f of x, already got it, but now we need to know what f of x plus h is. So every time we see an x instead, we're going to plug in x plus h, and then making sure that we FOIL out this binomial. So 2 and then x squared plus 2hx plus h squared minus 3. Then distributing that 2, we got 2x squared plus 4. I'm switching it. This looks better. xh. Yeah. Plus 2h squared minus 3. Now we can take those and plug them into our difference quotient. Right? So I want to know the limit as h approaches 0. 2x squared plus 4xh plus 2h squared minus 3 minus, this is a mistake I see a lot of people make, you have to put your f of x in parentheses because we're not just subtracting this 2x squared, we're subtracting the entire function. So we're subtracting 2x squared minus 3 all over h. Right? Obviously, we can't just do direct substitution here because we plug in 0 to not divide by 0. Anyway, we have to try to cancel that out. So first things first, we have to distribute this negative. When we do, we're going to have 2x squared minus 2x squared. So chop, chop. Then we're going to have negative 3 plus 3. So chop, chop. And then we're just left with 4xh plus 2h squared over h. Since both terms in the numerator have an h, we can finally cancel it, right? Boom, boom, right? That's because technically what I'm doing is taking out a greatest common factor, but this ends up being the limit as h approaches 0 of 4x plus 2h. And now we can finally do that direct substitution. So if I plug in 0 for h, you get that that limit equals 4x. What we just found was the derivative. That's super cool.